Okay, co-host. Okay, so please make Professor Deshmukh also co-host.
So I see that I'm already co-host.
Correct. Yes, yes. And then we need to give co-host controls to a few more of our colleagues who will join very soon.
Okay, very good.
So wait for
I
them.
think so. Both Professor Deshmukh and myself were both now co-hosts. Excellent.
Yes. So we are just waiting for some of our colleagues from IIT Mandi and IIT Madras. And then probably we can start soon, also on time.
Yes, we don't need to start before 5 o'clock. I just
Yes,
thought
yes.
I join early in order to
Right,
check.
right, right,
Sure.
right, right.
Um, Maybe I also try to share the screen just to see
Yes,
that
yes,
it's
yes.
fine.
Please go ahead. Please go ahead. Yes, please go ahead.
So I'll try it first. One option is to share the specific application. Then I need to see whether I can easily switch to full screen mode. Aha, so that doesn't work.
Perfect, sir. Perfect. Very nice. Very
Well,
nice.
just a second. We need to see whether it. Aha. So I think that's fine, right? You can see it in
Yes,
full screen mode
yes.
now.
It's full screen. It's full screen. Yes, we can see that.
Oh yes,
Perfect.
yeah, lovely slide. I think
Lovely.
it's
Fantastic slide, actually.
Okay, very good.
Very,
Then I'll
yes.
just stop screen sharing again, and then
Yep.
we can easily get back
okay.
to that
Sure.
later.
Sure.
Sure. Sure.
Um, so I would just put myself on silent, turn off the video until a few minutes before the meeting actually gets
No
started.
issue. No issue.
Yeah,
No issue.
yeah, that's
Okay.
fine.
Okay. Okay. Okay.
That's fine.
So I think Professor Shivram Krishnan also joined. Good evening. Good evening. Professor Shivram, are you able to hear us?
Yes, absolutely.
Okay. Perfect. Thank you for joining. Thank you so
My
much.
pleasure. My pleasure and honor.
So I think you can already see Professor Santra has already joined.
Yeah.
Professor Deshmukh is also there on the panel. So we are waiting for a few more of our colleagues to join, and then probably we can start at sharp 5 o'clock.
Yeah, absolutely.
Okay, perfect.
Oh, hi, Shiva.
Hi Pranav. How are you?
Wonderful to have you there.
Professor Hari Verma also joined. That's very nice.
Yes.
Okay, that's really nice.
Hari, are you able to hear us? Professor Hari?
Hari?
Hello.
Yeah.
Yes, Hari. Yes, Hari. Yes.
Yeah. Okay. So just to let Professor Satra know that Professor Hari is from IIT Madras IIT Mandi Physics Department, and Professor Shivram Krishnan is from IIT Madras Physics Department. And I think we are probably waiting for a few more of our colleagues, maybe, and then we can immediately start.
Robin knows Hari and Shiva both, I'm sure.
Yeah, I am guessing too,
Yes.
because of the Daisy affiliation.
Yes.
Yes.
And in fact, I requested.
Students are joining as we speak.
Hello, everybody.
Yeah, hello.
Hello, Robin. How are you?
Hi.
Robin.
Thanks
Hi.
for participating.
Hari, you can switch on your camera.
Okay. Yes.
So how has the seminar series been going so far?
Pretty good, I would say. We have had very distinguished speakers, and it's a great privilege to be able to listen to all of them. And the talks stay on the YouTube, and many visit the YouTube recording later. That is the advantage of this technology, because the timings, especially when we have a speaker from abroad, then the time zone difference makes it a little tricky to, fix the most convenient time, which is good for everybody. So there are about, I would say, about half of our speakers are from India, and the other half from different parts of the world.
So what would be your preferred seminar time? Is it always 5 p.m. what you prefer, or would early in the day have been preferable?
Yeah, our preferred time is a little bit earlier, more like 3 o'clock in the afternoon, Indian time. But for these special seminars, there's nothing like a very fixed time. And we had one seminar, I think, at 8:30 in the evening, right, Arijit?
Yes, that is correct. Yes.
We had one at 8:30 in the evening. We have one coming up at 6:30 in the evening. Tomorrow there is one at 5:30 in the evening. So the speakers are from different parts of the world and different time zones.
Yeah, absolutely. Particularly from North America, they probably want the evening.
Yes.
Presentations.
Yes. And especially those on the West Coast, it's very hard to find a common time because it's really gets to be tough.
Yeah.
I can see that.
Yeah. So 3 years ago, we had a conference, and that was right in the middle of pandemic. And it was essentially a virtual conference. and we had a sliding timetable. So over the 5 days of the meeting, we had the sessions at different parts of the day. On some parts, we chose timings which were convenient for participants from the East, from Australia, Japan, and then we had speakers from East, and then also all the way to the West Coast and the US. So it really was tricky, but it turned out to be a very nice conference.
Mm-hmm. Even though these online formats are a little bit difficult when it comes to true conversations.
Absolutely.
It's still a limitation.
Yes.
On the other hand, I do see the advantage of not traveling around the world so much.
Yes.
Certainly a bit of a plus.
Yeah.
I do.
The research seminars are a little more are relatively easier than actual teaching a class. If you're teaching a course, I think it is a disaster. But in a research seminar, at least everybody is involved. Most of the people are working in the field and they understand each other. But if you're teaching an undergraduate class and you don't see the expressions on the face of these kids, you don't even know if they are there.
Yes, exactly. Yeah, have you been able to do a lot of in-person teaching during the pandemic, or was it mostly online?
It was mostly online, but now it is quite some time that we have started having in-person classes and in-person meetings. So
we forgot that there has been such a thing as a pandemic.
Yeah.
For a lot of practical purposes.
Yeah, no, I haven't seen anybody using a mask for a long time.
Yes.
So either people are immune or reckless or both.
Yeah, let's hope it will stay that way.
Yeah.
But these talks are great, especially for us in India, because we have very limited travel budget and opportunity. So it's not even like we can attend every ICP for that matter. So having conferences in hybrid or online mode as well is a great opportunity. I try to catch up on the APS meetings and others, which is now hybrid, and so it's a great facilitator.
I agree. I can see that, definitely.
I think the biggest challenge is for the speaker, because he doesn't get to see the audience and the audience response and spontaneous questions face to face. So that is really unfortunate.
Right. Or sometimes questions that are typed in the chat.
Yes.
And as a presenter, one doesn't really check the chat all the time, so it's a little bit difficult to respond quickly.
Yes. So, Arijit, it is time. Do you think we should start?
Yeah, I think we can start now. We have So over to you, sir.
Yeah, thank you very much, and very hearty welcome to everybody for this afternoon's talk. We have a very distinguished speaker who is very well known to the community. And I'm requesting my colleagues, Dr. Shivram Krishnan and Dr. Hari Verma, to help us with this session. So I request Shiva to please introduce our distinguished speaker, and then Hari will conduct the session, the question answer session. Shiva?
Yes, thank you, Pranav. And it's indeed an immense pleasure and honor for me to introduce Professor Robin Santra. I'm sure there are many in this audience for whom introducing Robin is hardly even necessary. But then this is a diverse audience, especially young folks, students, and others. I would just say that I would be very surprised if you work in this field and you don't read one or many of Robin's works and can pass by. If you do, then trust me, you're missing something, right? So all that is largely because Robin has made remarkable contributions to this field. And although it's not a great thing to mention age, he is such a young scholar that one really looks forward to new works coming out of Robin's lab. And for a scientist of this eminence, it's only natural that the community recognizes him with a suitable range of awards, which I'm sure is a growing list. As of today, he is both a recipient of the IUPAP Young Scientist Prize and the prestigious US Presidential Early Career Awardee. In 2014, he was also elected a fellow of the American Physical Society. Of course, reaching these heights begins often with, maybe small yet noticeable beginnings. And this, in fact, began with his doctoral work at Germany's oldest university in Heidelberg. And for anyone working in clusters, I'm pretty sure people have come across his pioneering work on the interatomic or intermolecular Coulombic decay, where he, in fact, you can say, solved this remarkable theoretical problem where he integrated bound electronic structure based on a set of very special techniques. So this immediately led to a string of postdoctoral positions at prestigious and eminent labs around the world, beginning with GILA, the Joint Institute for Laboratory Astrophysics in the University of Colorado Boulder, and then at ITAMP at the Harvard-Smithsonian Center for Astrophysics. He joined the National Lab, Argonne National Lab in 2005 as a staff scientist. In 2008, he was appointed an associate professor at the University of Chicago. Currently, and from 2010 onwards, Professor Santra joined the Center for Free-Electron Laser Science in Hamburg as the head of the CFEL theory division. This is indeed a multi-institutional center, which is jointly funded by DAISY, the University of Hamburg, and the eminent Max Planck Society. His research areas are rather wide: theoretical, atomic, molecular, and optical physics. His works have made impression on chemical physics too and computational physics. He's particularly interested in X-ray induced processes, in ultrafast driven phenomena, applications of short wavelength free electron lasers, electronic structure, non-hermiticity in quantum mechanics. And I'm pretty sure those of us who have had the privilege of having interacted with Robin as a scientist, especially one-on-one, few-on-one, in a workshop or in a conference, especially in person, will more or less vouch for the instant impression of scholarship that Robin makes. And it's indeed a pleasure to discuss not just atomic physics, but any part of any branch of science, as I've discovered. So I can go on and on. You will certainly find his research details on his website, but then we are eagerly waiting now to listen to you, Professor Santra, on this colloquium as a part of this CAMOST-G20-S20 consortium. The floor is yours, Professor Santra.
So thank you very much for your very kind introduction. I'm almost a little bit shy now to give my presentation, but I'll do my best. So thanks a lot. And also thanks to the organizers, particularly also Professor Deshmukh, for inviting me to this exciting seminar series. So I'll try my best to make this interesting. Let me share my screen and see that we can.
Professor Santra, may I just drop in a word? If the audience wants to ask you a question, could they raise their hand during the talk, or would you prefer it at the end?
It's fine if someone wants to ask me questions. It could just be that you may have to tell me verbally if I don't pay attention to any raised electronic hands. But I have no problems with questions along the way.
So,
that's probably better than waiting until the end.
So then please raise the virtual hand or type in your question, both of which are welcome. And I think in the true spirit of online seminars, there are icons you can even possibly press to appreciate maybe points that you like. So you can use the emojis too. They wouldn't be very intrusive.
Okay, so I assume you can see the full screen now? Then I will...
Yes, your screen is visible. Professor.
Excellent. Very good. Okay, so in my presentation today, I will talk about science applications of X-ray free electron lasers, but in order to set the stage, I will give an introduction to X-ray science in a slightly broader sense. I will then discuss the technology that underlies X-ray free electron lasers, the sort of motivations that basically triggered the building of X-ray free electron lasers. So the areas of science that people are interested in connection with X-ray free electron lasers. And then I will move on and give 3 examples in which we've been involved in that indicate what sort of science applications have already become a reality. So as we all know, Röntgen discovered in 1895 those rays that in German we still call Röntgen rays, which are called X-rays internationally. And one thing to realize, and that will play a bit of a role in what I'll talk about, that when you look at very traditional applications of X-rays in medical diagnostics, you're actually looking at an application of the X-ray photoelectric effect. Often when we think and when we teach the photoelectric effect, we think of small photon energies and the statement that once your photon energy is too low, electrons cannot come out of the material. Well, with X-rays, you have such high photon energies that typically most elements in the material being exposed can undergo the photoelectric effect. So it's not a question of can it or can it not, but it's mostly a question of probability. That is, for low Z atoms, the X-ray absorption probability tends to be much smaller than the X-ray absorption probability for high Z atoms. And in fact, when X-rays are absorbed, say in our hand or anywhere else in our body, photoelectrons are produced, but we don't notice them because they normally get stuck in our tissue, so they don't manage to get out of our body. And the main reason they get stuck is, of course, because these electrons produced by the X-ray photoelectric effect lose the energy through collisional ionization events inside our body, mostly in water. So I will come back to that water topic later. And that's why they ultimately get stuck. And many particle hole pairs are produced per absorbed X-ray photon. Now, one can wonder, of course, if all elements, including, say, oxygen, carbon, nitrogen, can absorb the X-rays, why don't they do it? So why is it that it's mostly, say, the calcium-containing bones that absorb the X-rays, even though the lighter elements can absorb the X-rays just in principle, they could absorb them as well, because, again, the photon energy is higher than the binding energy, so it's not a fundamental impossibility. But the problem is the following. So if you think about it, under what condition can an electron absorb a photon? You quickly realize that a free electron cannot absorb a photon at all. So there is no such thing as a photoelectric effect for unbound electrons. So when you consider weakly bound electrons, that's kind of close to unbound, those have a fairly small X-ray absorption probability because they're close to kind of that free situation in which the photoelectric effect is forbidden. The stronger an electron is bound, the larger is its momentum uncertainty, and the larger the momentum uncertainty is, the larger the probability to absorb an X-ray photon. And that's essentially the reason why it's the innermost shells that have the strongest X-ray absorption probability, and the more weakly bound shells, the outer shells, have a smaller probability. When you then go to higher Z elements, electrons bound in inner shells have a particularly large momentum spread in terms of momentum uncertainty. That's where most of the photoabsorption takes place. And that's essentially also why X-rays are useful for element-sensitive detection, because through these inner shell binding energies, which are element-specific, we can distinguish then different elements, right? Either by measuring the kinetic energy of photoelectrons knocked out of the inner shells, or by measuring X-rays, spontaneous X-ray emission. Once an inner shell hole has been formed, an electron from an outer shell can fill the inner shell hole. You measure then the element-specific X-rays, or you can look for Auger-Meitner electrons. All of them carry, in principle, element-specific information. Now, I will talk a bit about applications of X-rays, not in connection with the photoelectric effect, but in connection with X-ray crystallography. X-ray crystallography does not use the photoelectric effect at all. It's not about having photons absorbed, but X-ray crystallography relies on X-rays being scattered. So the photons entering a crystal and in a sense being deflected and making it to the detector. Now, what you're seeing on the slide is the cross-section for various processes for carbon atoms. So it's the cross-section per atom as a function of the photon energy. When we're using crystallography, our goal is to figure out where do the atoms sit in a molecule. Say in biomolecular crystallography, as I'll state again later, you have to figure out how to grow a crystal out of the molecules you're interested in, so how to squeeze them into some sort of three-dimensional periodic lattice. And then essentially you have to use this process that people would in X-ray parlance would refer to as coherent X-ray scattering in order to form a coherent interference pattern of scattered X-rays. Now, if the goal is to find out where the atoms sit in the molecules, then you must view the individual atoms, so to speak, as slits, as if you're doing a grating, a scattering from a grating. Well, here the atoms serve, so to speak, as the grating. And the characteristic interatomic distance in condensed matter is about an angstrom. If you want to be able to see that in diffraction, the wavelength of the electromagnetic radiation you're diffracting off such an arrangement of atoms must be comparable to about an angstrom. And so an angstrom is, very roughly speaking, a photon energy of about 10 keV. So if we're looking here and going up, you see that the experimental cross-section, that's the individual circles that you might be able to see, that's basically still dominated by the underlying black curve, which is the photoelectric effect. So at 10 keV, most of the atom individually, they still prefer absorbing an X-ray photon rather than scattering the photon into the detector. The cross-section for the process you really want to use for structural imaging, so the cross-section per atom that underlies crystallography, that's this sigma coherent. And you can see it's about a factor of 10 smaller per atom than the photoelectric effect cross-section, so the photoabsorption cross-section. Another cross-section that is plotted here is sigma incoherent. That's basically what we would call the Compton scattering cross-section. So in that case, the photon does get deflected, but it does lose energy and transfers that energy to an electron and thus ionizes the atom. So cross-section for coherent and for Compton scattering, those two cross-sections are roughly the same, but the photoelectric effect still dominates per atom. Now, for some applications, as I've alluded to earlier, this fact that there is a photoelectric effect is perfectly useful. And this is an example, a very famous example from the 70s from Kai Sigwan's group, in which they basically demonstrated very impressively that you can use these element-specific inner shell binding energies that you can detect through X-ray induced photoelectron spectroscopy. You can use them not only to distinguish different atomic species, but you can even use them to distinguish atomic species of a given atoms of a given kind within a molecule. So this molecule, of course, is chosen to amplify the effect that I'm talking about. It's a molecule known as ethyl, so that's this part, the C2H5 rest. Trifluoro, so that's here the three fluorines connected to an acetate rest, right? So this molecule contains a total of 4 carbon atoms, and their inner shell binding energies, because its carbon atoms are all around 290 eV. You can very easily distinguish that from oxygen, for example, which has an inner shell binding energy near 540 eV. So, they're very far apart. but each of the peaks that you see here corresponds to one of the carbon atoms in this molecule. So you have what people call a chemical shift that indicates in which sort of chemical environment each of these species finds itself. So this is an important application of photoelectric effect with chemical sensitivity. But probably in terms of ultimate breadth of applications and impact, more important is X-ray crystallography, because X-ray crystallography has been the basis for determining protein structures. And most protein structures to date have been solved using X-ray crystallography. As indicated, you need an X-ray beam of sufficiently short wavelength, say about an angstrom or so wavelength. You want to bounce the photons off the atoms in the crystal of interest. You detect the interference pattern on a detector. Just one such interference pattern gives you literally two-dimensional information that's insufficient to figure out in 3 dimensions where the atoms sit. So you have to rotate the crystal and take another 2D snapshot. And this way you're assembling lots of 2D snapshots into a 3D diffraction volume, and then you invert the diffraction pattern in 3D reciprocal space to determine the atomic positions. The problem is, inorganic crystals come naturally as crystals. You don't have to work hard to get a sodium chloride crystal, say, but you have to work really hard to get a protein crystal. The issue is that typical proteins of interest might contain 100,000 atoms or so, and they do not come necessarily in exactly identical structures, and proteins do not interact with each other through strong chemical bonds. That's mostly van der Waals type interactions, and growing out of such molecules a 3-dimensional lattice is a challenge, and there's still a lot of molecules out there for which proteins specifically, for which the atomic structure has not been determined because people haven't figured out how to grow a protein crystal out of such proteins. So I was told that in some cases it took a decade or so after people decided to try to understand the structure of a given protein to grow a corresponding crystal out of that. So if one has succeeded in growing an adequate protein crystal, then you take the diffraction pattern. This shows one such 2D reciprocal space diffraction pattern. Again, you take many of those to assemble a 3-dimensional diffraction volume, and then you attempt to invert. I'm not going into the technical difficulties of inversion, but it's not uniquely solvable, because you're literally solving a problem in which you have lost half of the information. You know the intensities of the diffraction peaks. You don't know the associated phases of these diffraction peaks. And because we don't have the phase, one has to somehow recover the phase. Nevertheless, if one succeeds in solving this phase problem, one can recover these 3-dimensional electron density maps from which then these ribbon structures of proteins can be reconstructed for molecules of broad biological interest. Now, one reason, and I would say the main reason why we even normally do crystallography, is not because we care about protein crystals. So don't get me wrong, when I say we do protein crystallography and we have to figure out how to grow a crystal out of the proteins, we do that for purely technical reasons. No one cares about a protein crystal. It's just a tool, right? We care about the proteins, not about the crystals. So the issue is that if you grow a crystal, you can enhance the X-ray scattering through the effect of constructive and destructive interference. So as you know, when you have a crystal, constructive interference gives rise to the formation of Bragg peaks. So you're focusing the X-ray scattering into specific points in reciprocal space. As indicated here, you see these individual bright spots. Those are the Bragg peaks in reciprocal space where the X-ray scattering has been focused into. If you had an individual protein, and let's for argument's sake say you were able to scatter enough photons off an individual protein, the pattern would look very different. It would be completely smooth. There would be no bright spots, because the bright spots are a consequence of the crystal and not a consequence primarily of the underlying molecule. Now, that's one way how to try to address this problem, that X-ray scattering is fundamentally a weak process. Remember, photoelectric effect is much more likely per atom than X-ray scattering. So it's fundamentally a very weak process, and growing crystals is a pure technicality. The other technical approach to try to do protein crystallography, besides growing crystals, is to throw lots of X-rays onto those crystals. And an approach to get enough X-rays is basically accelerator-based production of X-rays. And at DESY in Hamburg, DESY is one of the places in the world where accelerator-based technology is used to produce high-intensity X-ray beams. Our flagship facility for applications such as X-ray crystallography is Petra 3. That's the so-called third-generation synchrotron storage ring. And that storage ring has a circumference of about 1 kilometer or so. It's large. Maybe in the background you can see the Elbe River that flows in this direction towards the North Sea. And here's the runway of the Airbus company. They have their own runway on the company grounds. We also operate a free electron laser in the extreme ultraviolet that's called FLASH. This has been available as a user facility since 2005 or so. And since 2017, we've been operating the accelerator for the European CFEL. I say it this way because the European CFEL, as the name suggests, it's really an international consortium. And DESY is the shareholder, the representative of Germany within that international consortium. And the specific task that DESY is fulfilling is actually the operation of the accelerator for the European CFEL. So that's the reason, which from a scientific perspective is maybe a little bit irritating, but that's the reason why the acceleration starts on the DESY campus and the experiments take place about 3 kilometers away from the campus. That means all the users that come there to the European CFEL to do experiments, they're 3 kilometers away from the campus and cannot so easily then interact with the scientists on site. Scientifically, it would have been nice to turn the whole thing around by 180 degrees, but again, it's because of a task to operate the accelerator, why it's operated this way. Now, let's look at this graph. This indicates to you how the peak intensity of X-rays coming out of different sources of X-rays has evolved over time. And specifically what we see here as, so to speak, one unit of X-ray intensity, Röntgen's first X-ray tube from 1895. So that's one unit. Modern X-ray tubes used for medical diagnostics are about 100,000 times brighter, about 100,000 times more intense. When you go to Petra 3, you have a peak intensity that's almost 18 orders of magnitude higher than Röntgen's X-ray tube. And when you go from Petra 3 to the European CFEL, you increase that peak intensity by a factor of about another 1 billion. And there are two main reasons why this is happening, or two numbers that cause this increase by roughly a factor of 1 billion. One of them is that in each X-ray pulse that comes out of an X-ray free electron laser, in comparison to a third generation storage ring, you have about 1 million or so more photons in such a pulse for a given bandwidth. That's, so to speak, one aspect how you get to a factor of 1 billion, 1 million roughly more photons. The other reason is why you have such increased intensity is that these pulses are much shorter, they're compressed in time. So you have a much more intense light pulse because you squeeze these photons into a pulse that's roughly a factor of 1,000 or more shorter than what you get from a facility like Petra. So at Petra, your typical X-ray pulses are roughly 100 picoseconds or so. At the European CFEL, you routinely produce X-ray pulses shorter than 100 femtoseconds, right? And when you combine these two effects, more photons squeezed into shorter pulses, it's therefore no surprise that you're able to bring up this intensity by basically something like a factor of 1 billion. Just a few words on how this lasing works in a free electron laser like the European CFEL. So this is illustrated by this graph, at least roughly. All these accelerator-based sources, FELs as well as third-generation synchrotron radiation sources, the way they produce the X-rays is by taking a relativistic electron beam and sending these individual clouds of electrons, right? Each cloud consists of a macroscopic number of electrons, and you send them through what is called an undulator. An undulator is a periodic arrangement of magnetic dipoles, which are arranged such that, say, in the first dipole, the electrons are displaced to the left when they move downstream, which is here to the right. So they're displaced, so to speak, into the plane first, and then in the next dipole magnet, they're displaced in the other direction. So when you look, so to speak, here from the right, you would see an electron cloud doing this. And so when you see an electron cloud doing this, then you say, oh, I see a Hertz dipole, right? So this is a Hertz dipole, even if it's not a free electron laser, you see a flying Hertz dipole that emits radiation. And all that radiation, because this is a relativistic Hertz dipole, is focused in the forward direction, again here to the right, with an opening angle of 1 over gamma, where gamma is the relativistic factor. Right? So if you have gammas of 10 to the 3 to 10 to the 4, you get into the millirad or so opening angle range, and that's why the beam is nicely focused. That you get at the storage ring too. And I should say that the periodicity of this magnetic lattice is roughly 1 centimeter. So you might wonder, why do you get then an angstrom wavelength out if you have a lab scale 1 centimeter? It's again a relativistic effect. It's on the one hand, from the perspective of the electron, that there is a relativistic length contraction. So they see an undulator length that's reduced by a factor of gamma. And we get another 1 over gamma factor for the wavelength because of the relativistic Doppler effect. So it's a source that moves relativistically towards us that leads to another blue shift. So with a gamma of 10 to the 4, we get from a lab scale of 1 centimeter down to 10 to the minus 10 meters, right? So from 10 to minus 2 down to 10 to minus 10 through 2 factors of gamma. That's what FELs and storage rings have in common, but what FELs have as their particularly specific mechanism is this process called self-amplified spontaneous emission. It's the fact that normally the electron cloud consists of electrons where the electrons sit in random positions. So because of the randomness of the positions, the radiation generated by such a standard electron cloud has a number of photons proportional to the number of electrons in that cloud. In other words, the individual electrons emit independently of one another, and the individual waves emitted by these electrons have no particular phase relationship with each other. So that's why you get an intensity out that's roughly linear in the number of electrons. That's the standard operation mechanism. That's what we use at Petra. Self-amplified spontaneous emission says, you know, if you have a really long undulator, then the electrons in that cloud can interact with their own spontaneously emitted synchrotron radiation. And when the electrons start interacting with their own light field, the electron bunch starts undergoing restructuring. And the electron bunch can undergo restructuring such that the electrons are no longer randomly placed in the bunch, but they start to undergo what is called microbunching. So you see here, you have random positions for the electrons at the entrance of the undulator, but as the electron cloud moves downstream through the undulator, you see here how the substructure starts emerging, and that substructure places the electrons at distance of a wavelength. Once they are all at distance of a wavelength relative to each other, they emit in phase. And when these individual electrons now oscillate in phase and their waves are in phase, the individual X-ray waves that they emit are in phase, then you get constructive interference. It's not the intensity that's linear in the number of electrons, it's the field strength that they generate that's linear in the number of electrons. That means the intensity coming out is now quadratic. Right? And that's basically why you end up getting an exponential gain in this region, because you have a macroscopic number of electrons, n, and you start having an intensity that's proportional to n, and as you run up here, you get finally an intensity proportional to n squared. And that gives you this enormous increase. That's why on a logarithmic scale, you get the linear increase, which is really an exponential increase. That's the lasing in an X-ray free electron laser. Now, there are three areas of application that people were considering and that have largely become a reality now that FEL X-ray free electron lasers are available. One of these applications that people were considering is to basically have a new way to look at molecular dynamics, femtosecond resolved chemical processes in molecular matter. This topic of femtochemistry is, of course, much older than X-ray free electron lasers, but in the past, the main problem was that the techniques used based on optical lasers, they're good for going into the femtosecond time domain, but they're not good for direct structural information. Right? Structural tools need something that directly is sensitive to structure. Photoelectrons are not very sensitive to structure, and one needs very elaborate calculations in order to make a connection between a time-dependent photoelectron spectrum and an actual structural change in a molecule. And basically, it has only been done for relatively simple systems. So with an X-ray free electron laser, now you have the ability to do snapshots on the femtosecond time scale and combine that with the possibility of using X-ray scattering for obtaining structural information. So this is what is indicated here by the snapshots of individual molecular structures. So this would be a way of molecular movie making. Then maybe the most compelling reason why X-ray free electron lasers have been built is this idea to do away completely with the need to crystallize the proteins. As I indicated earlier, there is no interest in protein crystals at all. They were introduced as a technique, but it's also a bottleneck because people have to figure out how to crystallize the proteins that normally don't want to undergo crystallization. The other issue is also that when you look at proteins in their natural environment, they are normally embedded in water and they actively undergo structural changes when interacting with other biological molecules. That's not exactly what happens in a protein crystal. So you would want to get away from the protein crystals. Now, why is an X-ray FEL a good way to go in that direction? Well, X-ray scattering cross-section is small. I can't change anything about that. Fine, that's just why it is. But we can fight the smallness of the X-ray scattering cross-section, or at least try to compensate for it, if we have more photons to send at our individual molecules. And as I said, we gain a factor of 1 billion in intensity or a factor of 1 million in photon number per shot in comparison to a storage ring, so that one can contemplate placing individual proteins into the X-ray beam and then detecting the scattering pattern from such an individual protein. And then again, you would have to take snapshots from different orientations to assemble a three-dimensional diffraction volume, which you would then have to invert, just like in crystallography. Now, from a theoretical perspective, and I'm a theorist, even though in the way I present my talk today, you might not guess that, but still, from a theoretical perspective, an important issue is that, yes, the pulses used and the pulses available from X-ray electron lasers are so short that as you're imaging the molecule, the atoms have very little time to move. So even though, as indicated earlier, the photoelectric effect is per atom very probable, and you're actually really significantly ionizing the atoms in such a protein, this protein will ultimately undergo an explosion. This is what this cartoon indicates. Every protein hit by an X-ray pulse undergoes destruction, complete destruction. However, the atomic displacements during the imaging process, during, say, the 10 or so femtosecond X-ray pulse, are negligible. So atomic displacement is not the problem. So in that sense, one outruns damage because one simply doesn't give the atoms time to move. But one must, of course, be aware of the fact that X-ray scattering is not scattering from atomic nuclei. It's scattering from electrons. And the electronic structure is modified by the X-ray photoelectric effect, by Auger-Meitner decay, by collisional ionization events, all of which do take place inside this protein as the imaging is done. So it will affect the pattern measured. That means one needs to have theory to eliminate from the measured pattern the impact of the radiation damage. Yeah, so the atoms have not been displaced, so that's all fine, but there is a modification of electronic structure one has to account for through theory. Then the third area of application is an area that simply says, oh, we like the fact that X-rays can induce a lot of damage or can deposit a lot of heat in a condensed matter sample through the X-ray photoelectric effect, and that's people who want to do laboratory astrophysics. That field is also called production of warm dense matter, as opposed to hot dense matter for fusion plasmas. So warm is in this case not to be misunderstood, because we're talking about temperatures somewhere between 10,000 degrees and maybe 100 million degrees. So I think whether one wants to call that warm, it's very much in the eye of the beholder. But you know, the people who labeled it warm come from the much higher temperature plasma community that wants to induce nuclear fusion. Anyway, the point is that for astrophysical objects that can exist under such high temperatures, the only reason they don't undergo immediate evaporation is, of course, is gravitational pressure. So if you look at a brown dwarf, say the interior of a brown dwarf at temperatures of 100,000 degrees or so, the reason it stays at solid density is gravitational pressure. So how can we mimic that on Earth? We cannot easily provide the pressure in order to investigate condensed matter systems at such temperatures. Yeah, we cannot provide the pressure, but we can do the experiment so rapidly that we can avoid the evaporation of the system and do our measurement before the system has had time to realize that it could normally evaporate under the experimental conditions that we have in our labs. So we use again the fact that we can do all these experiments on timescales below a picosecond. So we can produce states of matter that have condensed matter temperatures at temperatures in this temperature range, either by using the FEL itself or by using an optical laser. Now, if we use an optical laser to push a condensed matter system into this temperature range, then you would say, why do I need an FEL at all in order to do the experiment? Well, you need an FEL because otherwise you don't know what's happening inside. And why do I say that? It's because as soon as you've heated the material at condensed matter density into these plasma states, you have a perfect mirror. And perfect mirrors for optical light do not allow you to peek inside. Whereas X-rays have much higher photon energies than the so-called plasma frequency of these plasmas, that you can still peek inside such a condensed matter system, which an optical laser wouldn't be able to do. So you can still then use an optical laser to produce the plasma, but you look inside that material on sub-picosecond timescales with an X-ray free electron laser. Yeah. So this last topic I wanted to indicate because I think it's cute, but I won't talk about it in the following. I don't have a watch, so how much more time do I have? So now I'll talk about the things that we've been interested in more specifically.
20 plus minutes.
Okay, good. Thank you very much. Good. So now that you have a rough idea what people do with X-rays, at least from a high-level perspective, and how X-ray free electron lasers work and the sort of science applications that people have been considering, I'll show you two examples where the focus is specifically on the time resolve capabilities. So on the sub-picosecond pulse capabilities that allow us to follow fundamental structural dynamics in polyatomic systems. And the very first of these two examples I'd like to discuss is the birth of hydroxyl radicals in what is called the radiolysis of water. Now, the process of radiolysis itself, that's not a high intensity process. That's something that happens in low intensity X-rays. It's simply the fact that when X-rays are absorbed in water, say in our body, or other radiation, by the way, that ionization takes place such that H2O pluses are formed. And these H2O pluses somehow react then with neighboring water molecules, giving birth to hydroxyl radicals. And these hydroxyl radicals are highly reactive, and it has been estimated then that in radiotherapy, in which one wants to use the radiation to destroy tumor cells, that about 2/3 of the radiation damage is not because the radiation hit the DNA itself, but because of hydroxyl radicals produced in water that then interacted with the DNA, right? So in radiotherapy, it's, so to speak, a process that you want, but in other instances, it's not a process you want. When you fly across the Atlantic, you have a substantial radiation exposure, and that radiolysis and production of hydroxyl radicals happens in your body, and it contributes to your radiation dose that the body then experiences. Same, of course, even more so happens in space flight, in medical X-ray diagnostics. It also matters in corrosion in power plants that use water as a moderator. So all of them are affected by it. And the basic question that I want to address is, how does this fundamental reaction of the birth giving rise to hydroxyl radicals, how does it actually work? And how fast is it? Can we capture it with free electron laser technology? So here's a picture taken from a paper from 2016 in which you see timescales associated with processes. So somehow water absorbs a photon, and then H2O pluses are formed, electrons are formed, which ultimately undergo solvation, and these H2O pluses react with water molecules to form OH radicals and H3O plus ions, hydroxyl. Now, let's look at this here a bit more carefully. What this figure suggests is that about 100 femtoseconds up to about 100 picoseconds after a photon is absorbed or after ionization has taken place, these OH radicals are formed. And as we'll see, this is far off. In fact, the process is faster, and it takes about 50 femtoseconds, as I'll show you in a second. So this is quite misleading what was shown here. Now, how do we do this? This was an experiment that in fact does not use X-ray scattering or X-ray diffraction, but it used X-ray spectroscopy. And in a way that's very sensitive, practically background free. What do I mean by that? So you have liquid water, not individual gas phase water molecules, but literally a jet of liquid water. And inside this liquid water, radiation here, this is done with an optical laser inducing optical strong field ionization. So the radiation knocks out a valence electron. As soon as there is a hole in the valence shell, you can resonantly excite an electron from the inner shell into that hole, and you get X-ray absorption. When no ionization has taken place yet, so if this electron is still here, then this spot is blocked and you get no X-ray absorption. And this is what you see here. In blue, you see when no hole has been formed yet. So at this energy position, there's no X-ray absorption because there's no valence hole. And in red, you see what happens when a hole has already been formed. So you have either an H2O plus or you have an OH radical, and then you get this strong X-ray absorption. And so you can basically park yourself here at an X-ray energy of 526 eV and simply monitor that as a function of the delay between the ionizing pulse that forms the hole here in the valence shell. So this is this red pulse, and this delayed X-ray pulse that interrogates the valence hole formed. Right? So we interrogate the valence hole and look spectroscopically how that spectroscopic signature changes with time. So that's what you see here. We're zooming now into this energy range around 526 eV. You see here blue before the ionizing pulse has arrived because liquid water has no hole there, so there's no absorption. And then at 0, that's where the ionizing pulse is. Now we start having absorption. You see that at long times, this is a picosecond time scale, at long times this absorption disappears. That's because ultimately the hydroxyl radicals and the electron, they recombine. So you're filling the hole, you're forming OH minuses, and then the absorption goes away. But what we see when we look at very small time delays as shown here, so below a picosecond, and we carefully analyze the spectral line, we see that there's something happening in the spectral line on a time scale of about 50 femtoseconds. That's the signature of OH formation. So the birth of the OH radical takes place on this time scale. Now you will say, how can I conclude that? Because I can't see this by just looking at some time scale. It's just a time scale. At this point, it's not more than that. But I have to connect it, of course, to the underlying structural dynamics. And that's what we do through theory. So one of our codes, which is X molecule, is suitable to compute the electronic structure of molecules embedded basically in a liquid environment. And we can use that code also to compute the X-ray absorption signal as a function of some time delay after an initial non-equilibrium condition has been initiated. So what we see here is basically like this, but zoomed into shorter times. And because it's theory, we have much better time resolution than the experiment does. So you see here at near 526 eV, that the spectral line undergoes a time evolution with some time scale between 40 to 50 femtoseconds. You see, there's some redshift and then it goes back again. So there's something happening on these time scales that we recover in theory. And now the question is how these spectral dynamics that we see here connected to the disappearance of H2O pluses, so ionized water molecules, and the birth of OH radicals. So this is what you see here in these three structural snapshots. What is shown in black as a function of time after ionization is the average distance between oxygen atoms anywhere in our sample. So it's a fairly flat curve. Then we show in purple the distance between the water molecule that carries the hole, that is the H2O plus, and its nearest H2O. That shows a very different behavior, right? That's not flat, but it goes down. So you go from this roughly 2.7 angstroms down to roughly 2.4 angstroms. And then after 50 femtoseconds, you go back to the 2.7 angstroms. That's this. So something happens structurally on this 50 femtosecond time scale. That's what's shown here in these three snapshots. So what happens structurally is that this H2O plus, which carries the hole, this dumbbell structure is the 2p type orbital where the electron is missing. So this hole, because of its positive charge, it attracts the negatively charged oxygen end of a neighboring water molecule. So because this has a negative partial charge, it's attracted towards the H2O plus. In this way, the distance decreases. Once we are at this distance, we have basically no barrier to a reaction in which the proton is handed over from the H2O plus to the H2O. So at this point, we have optimal conditions for handing over the proton without a reaction barrier. That's when the proton transfer takes place. As soon as this H2O has grabbed that proton, then they separate again because the H3O plus is not attracted to the OH. So we go back again to our 2.7 angstroms. So here we literally watch then this handing over of the proton. The purple curve, as I said, shows you how the distance evolves as a function of time. The red curve shows you how the spectral line evolves as a function of time, right? The red is the spectral shift. You see how there's a red shift and again a blue shift. So these are directly correlated. So we see in the spectral shift the evolution of the environment of our initial H2O plus and the birth of the OH radical. So let me briefly acknowledge key people in this project. Caroline Arnold from my group did all the calculations, all the molecular dynamics and spectroscopy calculations. And the experiment was under the leadership of Linda Young from Argonne National Lab and Ziheng Lo from Nanyang Technological University in Singapore. Now, let me talk about another application of these structural techniques. And this is an investigation of a so-called conical intersection. Now, maybe you haven't heard about this, but there is a process in the human body in which such a conical intersection routinely plays a role, and it's the process of vision. So when light hits molecules in our eyes, retinal molecules in our eyes, you have a photoabsorption process in which a quantum transition from one electronic quantum state to an excited electronic quantum state takes place. Fine. But why does that molecule then not re-emit that light? When we think of atoms, that's typically what we have, right? Unless we have some sort of autoionization, typically what happens is that when you excite an atom, then all it can do is it can emit that light energy, that excitation energy, through light emission, through spontaneous emission. And in the optical regime, we're typically talking about lifetimes for spontaneous emission of around a nanosecond or so. Now, nanosecond is an eternity from the perspective of ultra-fast science, as the numbers I've been giving you in this presentation indicate. So if the system has a chance to dissipate the energy in another way, it will do it, particularly if that way to do it is faster than a nanosecond. And so what matters actually for a lot of what is called photochemistry is that molecules by and large have ways to dissipate the energy in a way that is way below nanosecond, so that spontaneous emission effectively gets turned off. And this is what happens through these conical intersections. It's this phenomenon that in polyatomic systems, there are normally structures at which excited and say ground state potential energy surfaces become degenerate. In fact, what you know from diatomics as avoided crossings in polyatomic systems with 3 or more atoms become true points of degeneracy. And this is significant because at these points of degeneracy, the so-called non-adiabatic couplings, which are the couplings that lead to the violation of the Born-Oppenheim approximation, they become infinite, they diverge. So that's why these conical intersections, you can see that this looks a bit like a cone. So this horizontal plane indicates the structural changes the molecule can undergo. The vertical change is energy, right? Electronic energy. So in this region, you have severe non-Born-Oppenheimer effects. And particularly when the molecule starts, say, in this area after photoabsorption, then this conical intersection essentially acts like a funnel and pulls the molecule into this region in its structural space. So it causes it to undergo a structural change and then go back onto the lower electronic state, and this way lose the electronic excitation energy, but ultimately all the energy released will go into vibration. So the system will get hotter, and typically it will have undergone a structural change, as is happening in the process of vision. Now, there's an entire class of proteins out there that are literally photoactive. That is, they absorb light and then they undergo a distinct structural change upon photoabsorption. And photoactive yellow protein, PYP, is one such molecule that goes from a so-called trans configuration. So you have a double bond and you have molecular ligands connected to the carbon atoms on either side of the double bond like this, and it goes to a cis configuration like that. And that sort of structural change is induced upon light absorption and going through that conical intersection funnel. But the funnel in the system like PYP is not a funnel as a function of 2 coordinates, as can be visualized, but it's a function of about 6,000 coordinates. It's connected to the fact that this PYP molecule has about 2,000 atoms. Each atom can move in X, Y, and Z. So you have about 6,000 coordinates. And that's so your plane, your 2D plane here becomes a 6,000 dimensional space. And still on top of that, you have energy, quantum energy of the electrons. And so the main challenge is to find a way to describe the dynamics in such a high dimensional problem in a low dimensional subspace. So finding effectively the relevant collective degrees of freedom that govern the motion through the conical intersection. And without going into details, we've done what I consider a fairly sophisticated way of looking at diffraction data. So this is all based on taking individual small crystals of PYP, using an optical laser to excite electronically to the first excited electronic state of PYP, and then as a function of the delay to measure the diffraction pattern with a high energy photon beam. So in this case, we're really looking at structure in reciprocal space, and we analyze the diffraction patterns, and we see that when you do a modal decomposition of the diffraction pattern of the dominant modes, that something is happening near 600 femtoseconds after the pulse. That's when the system here goes through the conical intersection, right? That's basically this point of conical intersection happens around here. And by analyzing this, we're able to fully reconstruct in this collective modal space of PYP the topography of the conical intersection. So we can, from this reconstruction, then see how the structural wave packet starts on the upper electronic state. So you have, before you go through the conical intersection, no probability of being on the lower electronic state, only being in the upper electronic state. Then as you go through the conical intersection, the probability of being in the upper electronic state decreases, and it starts building up on the lower state, because as mentioned here, you're literally going through the funnel and you're ending up on the lower surface. That's what this indicates here. So in this case, doctoral research in my group, Niels Breckwald, he did the calculations, particularly the quantum dynamics calculations of going through the conical intersection. And Abbas Urmat was particularly responsible for the machine learning data analysis work that was performed in this analysis of PYP and the characterization of the conical intersection of that system. Now, the last topic that I'll briefly would like to talk about is this question of molecular imaging of individual molecules. So I said earlier, when talking about the 3 areas of application people have been envisioning, is the idea of measuring individual proteins without the need for crystallization. That particular application has not been realized yet. At this point, no one has been able to image individual proteins, even with FELs, at atomic resolution. At lower resolution, people have done this for very large viruses and so forth, but not yet at atomic resolution. So one does not yet see atoms. But here I like to show you an example where we literally do single molecule imaging, but not for large complex molecules, but here for the example of iodopyridine, and I'll also show you results for iodopyrazine. So iodopyridine, in this case, what we exploit is that we have an enormous photoelectric effect. Instead of saying we want to insist on minimizing the photoelectric effect, again, we cannot easily influence that, and hoping for the best, here we simply embrace the photoelectric effect and everything that goes with it, and use the fact that we can ionize such molecules within femtoseconds, cause them to undergo an explosion, and we can then measure the momenta of the fragments. And the point here is, because the FEL causes such substantial ionization, that we can cause conditions in which every atom in the molecule is at least singly ionized. When you have such conditions, then you get perfect Coulomb explosion, the best conditions you can have. So panel B shows you the time evolution of the structure of iodo-pyridine. Iodo-pyridine has here in red an iodine atom. Then you see a ring that looks like a benzene ring, in which one carbon atom is replaced with a nitrogen atom. And you see here connected to 4 of the carbon atoms in gray, a hydrogen atom. And as this molecule gets hit at 0 femtoseconds by the X-ray pulse, then as time progresses, it undergoes an explosion. So first the protons fly away, then ultimately the carbons, nitrogens, and so forth fly apart. One interesting thing is that the carbon atom next to the iodine, if you look carefully, the carbon next to the iodine, because of the positively charged ring, it gets pushed towards the iodine atom, but because the iodine atom itself is positively charged, you get essentially a collision, bang, and the carbon then gets reflected backward to the left in this picture. Right? So ultimately, this carbon atom, therefore, acquires a negative momentum component along the horizontal axis. In panel A, you see the time evolution of the atomic momenta. And you see that these momenta converge very quickly within a few tenths of femtoseconds. You see the iodine momentum, you see in gray the hydrogen momenta, the nitrogen, the carbons, and this is specifically the carbon atom that got deflected. Even though, of course, this is momentum space, it carries a very substantial similarity to the initial structure even. You can identify from this momentum map each and every atom. Now what you see here with this femtosecond resolution is what we compute with our computational tools. So this is a molecular movie that has not been measured, this is what we compute. But what does one see in the experiment? Well, in the experiment, this is for iodo-pyridine. You see this panel is experiment. This is what we compute for the same condition in color. I'll say something about the black diamonds in a second. This is with the carbons. And again, here, the comparison with theory. And in the lower panels, we see the iodo-pyrazine. And it is actually quite remarkable. This experiment is done one molecule at a time. Each individual molecule, you have no clue how it was oriented, but you measure the iodine momentum, and you use for every iodine that you detect, every molecule that you detect, you use the iodine momentum here to define this horizontal axis. Then you measure a nitrogen ion, its momentum together with the iodine, they define the plane. And then you plot the hydrogen momenta, and you see here each individual hydrogen, H3, H4, H5, H6, directly in experiment. You see also each carbon atom, and through smart data analysis here, you can make each carbon atom nicely visible, the one that got deflected and the other four, C3, C4, C5, C6. So this is high quality Coulomb explosion imaging like nothing people have ever been able to do with other sources, with advantages that we can discuss later. So here I'd like to acknowledge from my group, Julia Schäfer, who has done all these ionization calculations and Coulomb explosion imaging calculations, and Rebecca Boll and Till Janke did the experiment at the European CFEL. So here's my summary. I don't think I'll have to read it to you. So I'm thankful again for having the opportunity to give this presentation, and I'm of course available for questions. Thank you.
Thank you, Robin, for this excellent talk, taking us through the wonderful world of X-ray science.
Thank you.
So now it is a time for question and answer session. So before that, maybe let me just make one small remark, since you mentioned Professor Linda Yang in the slides. So once, when I was working with Robin, and so Professor Linda Yang was the group leader at Chicago. And then she was talking to one of the visitors. So she said to that visitor that we are fortunate to have Robin with us because before touching the instrument, we know what number we can expect. So he's someone who works very closely with the experimental people. So he's a great scientist. So now it is time for, and in India, we are actually celebrating today Teachers' Day. So here we had the opportunity to learn from a master. So,
Thank you very much.
so it's
That's
time
very
for
kind.
questions.
Since I'm still around and I introduced Robin, indeed, the one line I missed saying is that Robin already has a very enduring sort of legacy around various corners in the globe. Many of his postdocs and students, both in India but also elsewhere, having academic positions, and that's really something remarkable in terms of moving for the scientific community. So maybe I will ask the first question. To Professor Robin Santra. Robin, thank you again for this fascinating talk. But then maybe this question was always motivated from what you were saying. We, of course, know experimental challenges in terms of achieving the ultimate goal of a single shot coherent diffractive imaging. Are there theoretical challenges too, which one sort of foresees in helping us understand either static structure or even in terms of doing calculating the dynamics? Could you share your perspective on that?
Yeah, so it's very difficult to do it truly from first principles when we're talking about systems that have a significant complexity. Even for something like iodopyridine, which is not a super large molecule, it's not, as far as is possible to say, not feasible to do a full quantum dynamics calculations. And the reason is simple, because ultimately, if you're talking about quantum dynamics and you want to be able to solve the tiny pinch Schrödinger equation, and we're talking about ionizing for a small molecule like iodopyridine a few tens of electrons, you would have to describe a continuum wave function for a few tens of electrons. It's already difficult to do even double ionization and to do that rigorously, especially if the electrons can interact with one another. For small molecules, of course, you could say that these ionization events are somehow sequential, so you may be able to separate them from each other. But ultimately, once the molecules become a little bit bigger, the electrons will inevitably start ionizing themselves. They will not just fly out happily and go to infinity, but they themselves will lose energy through collisions, similar to what I said about standard X-ray diagnostics. The photoelectrons in our body typically don't emerge from our skin, they just get stuck. And the same happens, in fact, in these proteins. Most electrons, relatively speaking, do not escape. So what happens is that most electrons remain trapped after a first few got emitted from the surface. You're building up such a large positive space charge that it becomes very difficult, if the electrons don't have MeV or so of energy, to escape from that large positive potential well, the deep potential well that gets formed. And so that means most electrons just get trapped by such an electrostatic potential well, keep colliding with each other, they start thermalizing, you get these temperatures of, say, 1 million or 10 million Kelvin. These little proteins are heated up into that temperature range. Doing all that quantum mechanically, rigorously, no one knows how to do it. So I would say that's a serious challenge, and we basically decided, okay, we don't know how to do it rigorously, so we decided not to do it rigorously. And so we started, of course, with atomic studies, where we do things kind of rigorously still in a rate equation approach, but that's still justifiable for FEL conditions, to kind of know what we're doing. And then based on this atomic understanding, we started treating polyatomic systems as ensembles of atoms. And literally we do calculations where in a polyatomic system, we compute for each atom how it individually undergoes changes, how electrons are ejected from the individual atoms, and all the ionized electrons in our calculations, when an electron is ionized, appear as classical electrons. Because we cannot afford to keep treating them as quantum waves, so we treat them as classical electrons. And so we have basically quantum calculations for computing cross-sections and the like, and Auger-Meitner rates and all that we do on the fly for all the atoms. But the atomic motion we treat through classical MD, and all the electrons that start popping up and appearing in the calculation, stochastically, I should say, we treat also through Newton's equations. And interestingly, every time we compare these calculations to experiments, it looks just like experiment. So I can't tell you why it works so well, but it works remarkably well. So in that sense, what I always considered a significant challenge, the fact that we don't know how to approach it rigorously and systematically, at least empirically, these non-rigorous approaches work quite well. If we then, however, ask, can we keep doing that sort of calculation for doing the full inversion process of really, you get the diffraction pattern for a protein, a molecule that might contain 1 million atoms or so, can we reliably do the forward calculation of the induced damage on the pattern? So in order to do the inversion systematically, not yet. That's because the way we do it is still a bit too inefficient. So there's still this significant challenge of making even the non-rigorous approach more efficient in order to have a really viable way of inverting. So we did a few years ago calculations on krypton 50,000 clusters. And even a single Monte Carlo trajectory, so just one stochastic realization of the ionization dynamics, took weeks. And that's just one, and that's just 50,000 atoms. And now we want to move towards 1 million, and we cannot do just a single Monte Carlo trajectory. We have to have a good representation of the stochastic probability distributions, which we don't get normally from just one realization. If each calculation took weeks or even months, we cannot feasibly take different molecules and quickly do a structural inversion, because it would take literally for every step in such an iterative process, each step might take weeks. So you see the bottleneck at the moment. This is a bottleneck that needs to be overcome. It's an unsolved problem so far. So I can't hear you anymore.
Sorry, can you hear me?
Yeah, now I hear you, yes.
Yes, would it be a smart choice to instead take maybe small crystals and reduce the FEL intensity and try and get away with single shot imaging? Would that strategy help us?
I mean, it's a possibility. It's a possibility in the sense that that's basically what people are doing at the moment. So what is called SFX, so serial femtosecond X-ray crystallography, does that. They use crystals that are much smaller than what you traditionally would have used at a storage ring. These crystals sometimes have in one dimension only something like 100 or so nanometer extension, maybe another dimension up to a micron. So they're really tiny, tiny crystals. I've been told that is actually already by itself a significant advance, because these crystals are so small that they tend to be free of, well, largely free of any defects. As you go to larger and larger crystals, you start accumulating defects, which then affect the quality of the diffraction patterns. These very small crystals are, on the one hand, easier to grow, unlike large crystals, and they tend to be fairly free of defects. So the diffraction patterns that people get from these tiny crystals tend to be of very high quality, I've been told. So yes, that is a way to go about. And they get really diffraction to sufficiently large scattering angle. That means to sufficiently large resolution, as people say, so that you get basically into the 1 angstrom regime. You can get good atomic resolution imaging. So yes, one can do that, and that's already FEL routine. That's what people do. The problem is it's still a limitation, because you still cannot do true molecular movies. You still cannot see how different species interact with each other, undergo substantial structural changes. You lose information about molecular individuality. What I mean by that is crystallography is seriously limiting, because all that gives rise to Bragg peaks is the average behavior of the molecules. So to put it differently, if we think of a quantum mechanical object in its time evolution being described by an actual wave function in a high dimensional space, depending on all the atomic coordinates, then the problem is that that means, in terms of individual, if you want, classical realizations, that one molecule in one unit cell, it could undergo a dissociation, and in another unit cell, it may not have undergone the dissociation, and a molecule in this unit cell might have undergone a single vibration. All of them are possible pathways associated with that one wave packet that each molecule can have. But it's not behavior that itself gives rise to a Bragg peak, because it's not periodic, right? Because this molecule did something, this molecule did something else, all of them being the same initial molecules, all starting from the same geometry, but their behaviors are not the same. And so only whatever you get when you average over all these behaviors is that net effect that you see in crystallography. And that's, of course, also misleading, by only being able to see this sort of average behavior, which is completely not what, in general at least, will be the dominant behavior. If, of course, a molecule does basically among 10 different possibilities, in 95% of all times, only option 1, and the other 9 are basically all suppressed. Fine, no problem. But it's not generally applicable and not generally a good assumption. So therefore, crystals are limiting us in this respect quite considerably. Another problem I should also say, but that's not so easy to overcome, is that the process of diffraction also limits us to pure pair distribution. So in other words, 2-point correlators. If there are any correlations that can only be understood if we have multi-body correlation information, not just I know that this is correlated with this, and this may be with this, but not simultaneously these three. Yeah? Say this motion affects this, and this is affected by the motion of the other two. It's not visible in the diffraction measurement the way it's done. It's not visible the way we measure diffraction patterns, so also that sort of information is lost. For perfectly static structures where each and every molecule has the same structure, that's not a problem. But that's not why we do FEL experiments. We're not interested just in these static structures. We're interested ultimately in what these things do. And whenever they do things, because they're ultimately informed by quantum information, quantum physics, they don't do only one thing. They normally have options, and they pursue them in a quantum mechanical sense. And crystallography is really bad in a way. I mean, I shouldn't say that so negatively, but it's a limitation of crystallography not to make it possible for us to actually see these things. If one comes from crystallography, of course, one doesn't think that way. One thinks immediately in these averages, but if one realizes that that's what constrains this approach, one then thinks, what are alternatives? This Coulomb explosion imaging technique I mentioned at the end is an alternative, because we do it one molecule at a time. And even at the moment, we can measure up to 8 ions in coincidence. So we can build, in principle, up to 8-point correlators in momentum space, admittedly, but there is so much correlation information in there that one could, with the help of theory, map that to spatial correlators beyond 2-point correlators. So I see potential there, and certainly because it's one molecule at a time, any of that sort of splitting of what wave packets might do is not averaged over, but you basically end up with one class that went the left way and another class that went the right way, and you capture them separately, and so all that averaging would not be applicable. But it's also not a technique one can apply to large proteins, for the reason indicated, because as you go to larger and larger systems, the majority of electrons that got ionized don't escape. That means for Coulomb explosion imaging, you want to basically make sure that per atom about 1 electron literally escapes, which was the case for iodopyridine. So the whole molecule had a charge of higher than 10 or so. Perfect explosion, the best one can get. Large protein won't happen because a tiny fraction escape, and you basically get a plasma ball that behaves not like a Coulomb exploding object, but more like a hot hydrodynamic droplet. So it's unsuitable for Coulomb explosion imaging, I'm afraid. So I couldn't hear you. You were maybe saying something. I can't hear
Are
you.
there any questions? Any other questions?
Yeah, Professor Robin, myself Sunil. Yeah, I have a question regarding that OH radical formation.
Yes.
So you said that the OH radical is one pathway of damaging this kind of proteins or other in DNA, for instance. But also the photons can actually photo dissociate these molecules. So there are these two channels which can be considered to be destroying this molecule. So is there a possibility that one can gain an understanding of how much is one process probably more probable compared to the other?
Yes, so people have estimated this, and this is basically based on, how much water do you have around DNA, so how much of the absorption would take place for a given X-ray fluence in the water, and how much direct ionization you get. In principle, it's something that's not difficult to compute, just where the absorption takes place, because the individual absorption cross sections are dominated by inner shells. That means it's just a matter of knowing inner shell cross sections and counting atoms. So getting relative probabilities just where photoabsorption takes place is not difficult, just based on knowing what atomic ratio you've got for the different species. So based on such things, and also some measurements, people have estimated that it seems that in radiotherapy, it's about a 2-to-1 ratio of OH-induced damage to direct damage. Now, this is all a little bit also not complete. As I said, in terms of direct photoionization, I think one can be pretty safe in terms of estimating how much ionization you get. But of course, ionization is only the very first step. And I'm only talking about the photoabsorption. In fact, the vast majority of the electron hole pairs that underlie radiation damage in this OH context is not by the photoabsorption process itself. Say if we expose ourselves in radiotherapy to actual X-rays, and an X-ray photon is absorbed in one of our cells, basically the binding energies, the inner shell binding energies in our atoms, in carbon, oxygen, nitrogen, they're all way below a keV, and the photon energies typically used are normally much higher. So that means the photoelectron produced carries then practically all the energy. Right, so if you take, for argument's sake, a 10 keV photon, you're producing basically a 10 keV photoelectron, and most of the damage then in the body, in the cells, is caused not by the photon. It was ultimately triggered by the photon, but ultimately it's caused by the photoelectron produced. That's basically what I indicated, that there are photoelectrons produced, but they don't come out because this 10 keV photoelectron travels through our cells. And basically, after a nanometer or so, it ionizes a first electron. That means it produces the first particle hole pair, typically giving that particle hole pair very little excess energy. In other words, it just ionized the electron. The ionized electron produced will be a low energy electron. It means typically, say, the 10 keV electron in this first collision will lose about 10-ish EV. Right? And then it will keep just doing that. So if you go in with 10 keV and each particle hole pair requires an excitation energy of about 10 EV, you can produce per initially absorbed photon, and therefore per produced photoelectron, about 1,000 particle hole pairs. And each of these particle hole pairs will be spread out over a volume that's much bigger than the region where the photon was absorbed, because you have this kind of quasi-random walk of the photoelectron traveling around and, losing energy along the way. So if it went along a straight path, for argument's sake, and the mean free path around those energies is maybe a nanometer, then the electron might go up to 1,000 nanometers or so. So maybe up to a micron. So you might think that even if you have fairly localized ionization, up to a micron could be the extension of the impact of the damage caused by the absorbed photon. And then from each of these particle hole pairs, you're producing OHs. From each of these particle hole pairs, you've also produced these free electrons so the ionized electron, of course, also then becomes solvated, and it itself is reactive and also does contribute to radiation damage. So ultimately, if one looks more carefully, also looking at other species present in cells, there are more reactions taking place. This OH process is, and the production then of an electron that ultimately gets solvated, it's just one that starts it all. It's one of many. And the main question is, can we disentangle then? And I think that's really where your question goes. Can we truly disentangle these steps as they really take place in real time and really take place in a cell? And I would say at this point, not yet. At this point, we're still trying to develop essentially what you could call model systems, simplified situations in which maybe we have just liquid water. More recently, we've been looking at fairly concentrated solutions of urea in liquid water. And we've been looking at proton transfer reactions in that case. So, it's a bit of a building up process in which one tries to systematically increase complexity and draw conclusions from that. But to really do this in the more complex environment of a cell, in the presence of, say, DNA in water, but also the presence of all the other reactive agents and the other molecular species that are there. It's not that a cell is only water and only DNA, right? There's so much more going on. And all of that, when one talks about the ultimate impact on DNA, would require taking everything else also into consideration, because we're no longer talking about purely ultra-fast timescales. I talked about the birth of the OH, but what about then the time scales it needs the OHs to actually drift, to diffuse towards the DNA? This is not ultra fast. It will take a while. It might take nanoseconds or so, but once one goes to these much longer time scales, suddenly other processes can come into play and may interfere with whatever the OH would be doing. This is, I would say, one of the biggest challenges we have at the moment, how to meaningfully bridge the insights from ultrafast, where we really get detailed mechanistic insight, to the sort of long time scale measurements that people have been doing in chemical kinetics for decades, literally, where typically you don't get much of a detailed understanding of what's going on. You only see the slowest processes, basically, and from those, then with a lot of guesswork, you try to piece together the detailed mechanisms. But how to really get, so to speak, the whole picture, including later processes, which were kind of slowed down by an earlier bottleneck, but may themselves again be fast. We don't even know how to observe them at the moment, because we don't know how to trigger them with femtosecond precision. So these are unsolved problems in a much broader sense than even the OH reaction problem.
Okay. Yeah. Okay. Thank you. Thank you very much for the explanations.
You're welcome.
Any other questions?
I think we should encourage people to write to Robin if they have some more questions now.
So
Absolutely.
I have just one question. So for water molecule, this ICD pathways have been reported recently. That's for the synchrotron radiation. So what about for the free electron laser? What is the ICD pathways?
So one would not expect that fundamentally the pathways would be different at an FEL. The FEL does only two things. Either you use the full intensity of the beam. In this way, the concentration of ionization events, right, the number of particle hole pairs per unit volume, can be made much bigger than what you get at a storage ring. So that's one way how an FEL experiment can differ from a storage ring experiment, but that's a question whether you're doing the experiment under these conditions. So you don't necessarily have to focus the beam down to 100 nanometers. With an FEL, it's possible, right? Nothing keeps you from doing it. It's an option available at FELs like LCLS, so you can have submicron focus. And when you go to submicron focus, you can basically get an absorption density that goes in the direction of, maybe, depending on the system, in water, you might easily get into the, say, 10% range for photoabsorption. But then each photoelectron, as I said, will cause ionization through collision. So you just turn this into a plasma locally, no problem. Then you're asking me, so how important is ICD? I tell you, it won't be very important, because you've just dumped all that energy into the system, and there will be all these collision ionization processes. So if I push it into the super high intensity regime, I think what one has learned about ICD from low intensity sources is not directly applicable, because there are most likely more important competing processes from this large number of electrons flying around with high energies. However, as I said, per se, that's not a necessity. You can also not focus your beam so much, and then you immediately bring the concentration of particle hole paths down into a regime where the interaction among the particle hole paths may become largely negligible, at least on maybe a picosecond time scale, largely negligible. And then you might see precisely the same things that you see at the storage ring. That's one aspect, intensity. The other aspect is time resolution. What is difficult at storage rings, because the pulses are practically eternally long, right? 10-ish to 100 picosecond X-ray pulses are too long to directly time resolve ICD-related dynamics. Typically, even the electronic decay processes, especially if we're looking at condensed matter, are substantially below picoseconds, and any ensuing structural dynamics would also be fast. So 100 picosecond pulse, in order to observe such dynamics, to trigger and maybe separately observe, would be suboptimal. Right? You see kind of the outcome, and that's it, not really following the process. So if you want to be able to follow the process in a pump probe way, you want to have a source for pumping and a probe for interrogating, where each pulse is maybe only 10 femtoseconds or so long. That would be an opportunity at an FEL. It's not so much that I would expect that the fundamental physics of ICD would be FEL specific, even though I'm not ruling out that there can be some effects. But just generally speaking, I would think an FEL could be a good way to look more into ICD related processes, just because they're really good at getting good time resolution. I haven't really kept up so much, I should immediately admit, with the sort of ICD investigations that people have been doing in FELs. There may have been some, but nothing that really caught my attention, I must say. Yeah, so ICD is, of course, something that one also must factor into questions of radiation damage, ICD as a source of really low energy electrons. I tend to be a little bit reluctant to highlight it too much, because the statement that, upon initial ionization, then at some stage you're producing ICD electrons, that's true. But per initial hole, typically you're producing very few, one or so. Whereas I told you, the photoelectron that I produce with X-rays produces 1,000 particle hole pairs. So if I compare them, if I just look in terms of sheer numbers, the main damage really doesn't come from the ICD electrons. It really comes from the particle hole pairs produced by impact ionization. However, having said that, I cannot say that each individual particle hole pair produced through collisions could not also, to some degree, undergo ICD, because the collision ionization by the photoelectron might produce holes that are not at the top of the valence band. It might also be deeper, going into the inner valence. So there may be an additional component that goes beyond the initial, ICD, where, so to speak, the initial photoabsorption takes place. I think there could be a substantial contribution from ICD where the photoelectron knocks out additional electrons, so where it produces additional electron hole pairs. And I think that has not been really investigated as far as I can say. So it's an open question, in my view.
Thank you, Robin.
You're welcome.
I think if they have more questions, then maybe you can write to Robin.
Yeah, you're welcome to write to me. So I'd be happy to answer any questions that remain.
Okay. So thank you once again, Robin, for this very excellent talk. Maybe I'll hand over mic to Professor Deshmukh to conclude the session.
Amazing. It had everything from chemistry to biology to life, to technology, engineering, fundamental physics. Awesome talk. Really enjoyed it, Robin.
Thank you very much.
Thank you very much. And goodbye for now.
Goodbye to all of you. So thanks so much for attending the seminar. Goodbye.
Goodbye. Thank you.